can be done, especially if you want to repeat this for your research purposes. It's amazingly efficient to do it this way. We're all geotechnical engineers. Let's worry about another important problem, which is consolidation. The consolidation, we all know, is important, and we know the 3D consolidation equation, I hope. And suppose we want to model consolidation in a centrifuge. We know from our basic soil mechanics that what controls consolidation is the time factor TB. So this depends on your coefficient of consolidation, which is for the given soil, you know that, and the time for achieving that particular degree of consolidation, and D is your drainage path. Right? We all know that. And typically what you should aim for is you want the same degree of consolidation in your centrifuge model as you have in the field, because you're trying to create the same soil model, right? Now let's see how long it will take in the centrifuge. So how much is the T going to be, the small t? So I can write the same equation for prototype and model, and the left-hand side should be equal if I want the same degree of consolidation, right? So if I divide one with the other and use the same soil, then I can also cancel, hopefully if I'm using the same soil, the CV is the same, because that's property of the soil, right? So we can get rid of that. So we'll be left with just the right-hand bit of that equation. And it turns out that the scaling law for consolidation comes simply as 1 over n squared. This is fantastic news for us. Why? Suppose I got, say, a 10-meter deep marine clay in Bombay. Typically, it will take about 10 years to get to 90-95% consolidation. I'm not too far off the numbers, I hope. Now, if I want to model the same 10-meter equivalent thickness in the centrifuge at 100 G, then the time it takes in the model will be simply 10 years times 365 times 24 hours, 60 minutes, 60 seconds, divided by 100 square, right? That's what we're applying that equation for. Then, if I do the numbers, it turns out it is about 9 hours. So if I run my centrifuge for 9 hours continuously, I can tell you how much settlement your 10-meter thick clay layer will have at the end of 10 years in 9 hours. What do you call such a machine? Which can tell into future what's going to happen in future. We call a time machine. So it started with a centrifuge, ended up with a time machine, as far as consolidation is concerned. Okay, and it's also true for many diffusion problems. It can work in your favor. There are some cases where it won't work in your favor, especially when it comes to earthquakes. And I'll pick on that and then very swiftly move into pile foundations tomorrow. So we kind of touched the pile foundations. I done a bit of sheet pile walls and a bit of piles today, and that's kind of deliberate. But I'd certainly we have all the basics now to look at why we have to study these problems so carefully with all this gadgetry. But at the end of it all, what's important is the soil mechanics, the geotechnical behavior of these things. The rest of it is just a way or means of getting that knowledge or understanding the behavior. Okay? Right. I'm going to stop there and I'll pick on the rest tomorrow. Any questions, by the way? Yeah.
So in centrifuge model, let's say I want to see the behavior of Button dam. How will I see the construction locale? Like levels, I want to see the post pressure development.
Yeah, good question. we have any construction process you can think of, making it in the centrifuge. A simple starting point would be to make the whole dam in the lab floor, put it on the centrifuge and spin it, right? But of course, that won't get what you want, clearly. So if you want to simulate the construction of the dam, what we have is like a hopper on the top of the model, which will go and pour the embankment while the thing is spinning around. So although I'm talking about just the earthquake actuators, because we are going to focus mostly on earthquake actuators, we have lots of other gadgets like robots, which will operate under G and do this construction. We did the Nicole Highway collapse, where we had to have props at 3 levels and excavate in between. And we can program it in. That's why it's fun to do these things. We can do that.
You can also compact it. Yeah?
You can, if you want. You need a compactor to run. I mean, if you come as a PhD student, that's probably what you will do. You know, at the moment, we have a student who is trying to build a TBM, a mini TBM, which can bore like the ones I've shown you. So, as I said at the beginning, one of the biggest things we don't know is what happens to all these big structures we have in London when we are making these tunnels underneath existing foundations. And there's no soil mechanics theory to say it's all going to be okay or not. You know. So, yeah, that's fun. Geotechnical engineering is fun. Yeah.
Scaling of particle size, soil grain size.
Yes. Actually, yeah, that would take a few minutes to explain. Shall I take the time now or shall I come? I think it's probably a good idea to do this. I actually jumped off that. There are a few things which I'm deliberately not. It's a very common thing people ask is you're scaling the structure like piles or retaining walls down. How come you're not scaling the particles of the soil down? And this comes, the proof for this is actually a logical proof, and I'll run by you with this. The first thing is to say, if you are a numerical person and you've been using finite element analysis, you never complained that your elements are all triangular and rectangular while your real soil is actually grains. Why do you think that's acceptable? The reason it's acceptable is underlying all this, we believe that there is continuum mechanics at play, and the continuum mechanics is what governs the soil behavior. We know it is a particulate material at each particle level, but because we are not dealing with one particle, we are always dealing with thousands of particles, it can behave like a continuum. That is a common assumption throughout soil mechanics. Same for triaxial, by the way. So from that point of view, it's right that we are not scaling the particles down. Second point is that there is enough research now to show that what governs the soil response, say with respect to the pile inside, is how big is the pile compared to the mean particle size, say D20. So if my ratio of my pile to D20 is a factor of 50 or 100, it doesn't matter how much that ratio is beyond that. It'll behave exactly the same way. And this is because guys like Fumio Tetsuoka have the formation of the shear bands. They measure the thickness of the shear band, and the shear band is typically about 3 or 4 particle diameters wide only. And what happens is the shear band thickness is what controls the ultimate failure mechanism. So the important thing is when you're testing piles in a centrifuge, don't get carried away and say I got 0.5 meter diameter pile. Now, if I do a test at 50 G, then the size of the pile is 5 millimeters. If I do a test at maybe 25 G, it's 10 millimeters, right? So what I need to do is to choose the G level so that I have enough ratio between my mean particle size and that pi. Say if I'm testing in clay, because the clay particles are so fine, this ratio usually does not come into play. It's only for sands, and that to coarse sands you need to watch out for. And that's what all centrifuge modelers do. So you decide on the G level depending on the size of the model structure you're going to test. Maybe, another way to say this is, if I increase the G level, eventually your pile is going to become like a knitting needle. Now, we all know if I have a needle, I can push it into sand with no trouble at all. But then the ratio of the particle size is probably bigger than your needle size. Therefore, that ratio will fail. Okay, so those are the minimum things you need to do. There is obviously a limit on what is the G level and what type of structures we can test. But logically, I think we are quite right in saying not to scale the particles. If you scale particles, the other problem is you need to prove, the burden of proof falls on you to say that whatever material you have picked has the same constitutive behavior as your prototype material. Whereas here we don't bother. We use the same material from the field, then we don't need to know anything about the soil. Only stress history we need to know. Yes, but you work with the worst ratio. If you satisfy it for the, you will satisfy for everything else. Yeah, that's something we're getting into. We're making more and more layered soils tests now. Any other questions? Yeah.
How is the permeability of soil scale?
Right. Actually, it's a good point. I wanted you to do some homework. Are you game for it or no? Yeah? Right. Maybe I want you to think a little bit about these things. I ran something similar in Kyushu University, but I'd like you to give me 1 second, sir. Thank you. So I'd like you to do the second question here, which is derive the scaling laws for shear force and bending moment, because we haven't covered that in my lecture. Yeah? And also for any impulse loading. Again, that's something we haven't done in my lectures. So how do you derive? Based on what we learned today, and using any physics knowledge you have at the back of your mind, I want you to derive scaling laws for these two things. The other ones I'll explain.
Probably this question can be taken as a tutorial for the next.
Sorry?
Second question, maybe let them solve the after the breaks.
Okay, fine. I'm hoping to leave, so maybe you can discuss and you can tell me tomorrow.
Yes, sir. This one is for your tutorial class today. After break, you can try to solve this problem. Using the simple what process I highlighted.
Just write down this question.
Hmm?
Just let them take the question.
Yeah, I'll leave it on. Talk like this, and somebody has a task about particles.